as always, we can start by thinking about the expression that we have for the break. So which one of these three electronic structures do you think that has more one-hot singularities? Again, one-hot singularities are energies at which your density of a state is simply divergent. So thoughts? Yes, absolutely. Yes. So, and somebody say why? Yes, yes, very, very good. And I will actually phrase it as it has more bands. So you can think that each band can contribute with one one-hot singularity, or maybe two, or maybe three, depending on the electronic structure. So if your electronic structure has, let's say, 2 minibands, you may have at least 2 one-hot singularities. If you have 4, at least 4. You have at least 100 bands, at least 100 one-hot singularities. All right, great. So now let us move on to the electronic structure of twisted graphene multilayer. So far we've been focusing on the simplest twisted van der Waals materials in terms of the electronic structure. So far we essentially consider that we have one 2D material that had electronic state, and that the other 2D material essentially created the potential in this original 2D material. But very often when we create a twisted van der Waals structure, the electronic states can live in 2 layers simultaneously. And this is something that happens in general if you have graphene multilayers, because they are certain metals, they have states at all the energies, and therefore the moire states are likely to live in all the layers at the same time. So let's start with the simplest graphene multilayer, and then later on we are going to go to a little bit more complicated graphene multilayer. So the twisted graphene multilayer is twisted bilayer graphene, that you essentially have 2 layers. You have 1 layer on top and 1 layer on the bottom. And again, you twist one with respect to each other. The twist angle controls with the length scale of the moire. And where it's going to be very important for us now is that when you twist in real space, you also twist in reciprocal space. So you can think about how is the Brillouin sum of 1 layer with respect to each other. And therefore, so if you twist one of the layers in real space, then the Brillouin sum of that layer is also going to twist in reciprocal space. So in particular, in graphene, we know that we have Dirac points at the K and K prime points. So when you twist in real space, you are essentially going to get Dirac points that have a certain momentum difference in reciprocal space. So again, one of the things that is going to become important later on is that in this twisted graphene bilayer, we essentially have 3 different regions that we can identify in terms of stacking. There's the AA stacking, and there's the AB stacking. And of course, the twist angle controls with the distance between AA stacking, and the twist angle, of course, controls what is the emergent lattice constant that we get from the moire. So again, just a reminder about the electronic structure of graphene. So this is the band structure that we get for monolayer graphene. We have 2 Dirac points, 1 in K and 1 in K prime. That essentially are the corners of the Brillouin sum that I showed you before. And the basic idea is that around these K and K prime points, we essentially say that our Hamiltonian is a Dirac equation, is a Dirac norm, in which we have a linearly dispersing things. So this is, yes. In principle, no. So the distance between the layers is essentially defined by the van der Waals force, and the twist angle doesn't change too much. What is the distance between layers? There's a teeny tiny difference of something. I think it was something like 1% or so, but almost insignificant. And this difference essentially comes from the fact that from AA stacking, from AA to AB stacking, van der Waals forces change a little bit, but the effect is very small, and it doesn't happen something like the electronic structure. Yeah, thanks. That was a very nice question. All right, great. So this is the electronic structure of monolayer graphene that we are already familiar with. So now let's take this twisted graphene bilayer, and let's first remind ourselves that the Brillouin sum essentially consists now on 2 original Brillouin sums rotated with respect to each other. So red Brillouin zone corresponds to one of the layers, blue Brillouin zone corresponds to the other layer. So we are going to have here cones from one layer and the other layer in different points of reciprocal space. And from the point of view of how we can, let's say, solve this model, we can use the very same high-bounding model that we've been using so far. So we can consider that we have one orbital per carbon atom, and we have, for example, first neighbor hopping within each layer, and then to couple the different carbon atoms in the different layers, we essentially use some distance-dependent hopping that it can be parameterized in some Slater-Foster form. So essentially a hopping that has an exponential dependence. So the farther apart your atoms are, the smaller the hopping is. So essentially the model that we need to use to solve this with the graphene materials is very much the same high-bounding model that we've been using for other systems. And of course, this is the model that we are going to use during the exercise section for the electronic structure of twisted graphene layers. And then something that is going to become important later on is that in these twisted graphene bilayers, we can also apply a bias between the layers. And by bias, essentially what I mean is that one essentially applies the voltage in the perpendicular direction. So electrons in one layer have a different energy than electrons in the opposite layer. And in terms of a high-bounding model, this essentially means that the on-site energy of electrons in one layer is different from the on-site energy of electrons in the other layer. So now let's look at how the electronic structure gets reconstructed as we twist the two graphene layers. And to start with, let us just consider that I'm going to take the two graphene bilayers completely decoupled. They are twisted with respect to each other. So I will see the electronic structure of the two layers simultaneously, but there's no coupling between them yet. So the basic idea is that if you don't have any coupling, then the let's say the cones of the two layers are going to appear in different points in momentum space, right? And this is just a consequence of the Brillouin zone of the two monolayers being rotated with respect to each other. So this would be K of one of the layers, and this would be let's say K of the other layer. And if you now think in terms of the Brillouin zone of the supercell, this would be K and this would be K prime. So the basic idea is that the rotation angle controls what is the rotation between the two Brillouin zones, and therefore the rotation angle is going to control what is the distance between your cones in reciprocal space. So the smaller your rotation angle is, the closer the corners of the Brillouin zone are going to be together, and the larger the rotation angle between the two layers are, the farther apart the corners of the Brillouin zone are going to be with respect to each other. So this is how the electronic structure looks like without any coupling between the layers. But if you now start increasing the coupling between layers, what you actually see is that you are going to get anti-crossing in your electronic structure. And in particular, this anti-crossing is going to be proportional to the coupling that you have in between the layers. So if you take, for example, the real interlayer hopping and you take a very large angle between your two layers, you are going to end up in a situation in which there's an anti-crossing here, but you still have Dirac cones at low energy. The interesting point is that even in this situation at very large angles, what you actually see is that your hopping changes a little bit the Fermi velocity. So it changes a little bit the slope of this Dirac cone, just because, well, if you have an anti-crossing, then you have to pull your states down a little bit. So this is what is called the Fermi velocity of renormalization in twisted graphene bilayers. And this is essentially what happens if you are at angles that are above 1.5 degrees. And you can start seeing this effect around, let's say, 10 degrees or so. So the smaller you make your angle, the stronger the velocity of renormalization is, and the lower the Fermi velocity. And this is something that you can see if you kind of decrease the distance in momentum space. So if you decrease the distance in momentum space, essentially the anti-crossing is going to take the same value in terms of energy, but now your states are going to be flatter than before. So in other words, as you take smaller and smaller angles in a twisted graphene bilayer, and you are, let's say, above 1.5 degrees, then your Fermi velocity becomes smaller and smaller and smaller. And eventually, of course, if you are in a very fine-tuned case in which your distance between Dirac cones or formed Dirac cones is exactly the right one, so that the interlayer coupling creates an anti-crossing that is completely flat, then your Fermi velocity would be technically zero, because the Fermi velocity of a flat band is zero. This is what is called the magic angle in twisted graphene. Let me emphasize that this kind of game works if you have electronic structures from two materials, right? So before we were just thinking about the electronic structure of a single monolayer influenced by the other, but now if you have two Dirac cones coming from two different graphene systems, then you can play this game of looking for the interlayer hopping that essentially makes your band completely flat. So this has many interesting consequences. And the first consequence is that the regime in which your flat bands appear depends only on the ratio between the interlayer coupling and your angle. Or in other words, what this means is that if you make the interlayer coupling twice as big, then your flat band is going to appear at an angle that is twice as big. And even though we may think that, well, increasing interlayer hoppings is not easy to the materials, it is actually doable in certain instances. And for example, people have seen that the physics of twisted graphene bilayers in certain regimes can be reproduced at higher angles if you just apply pressure over the two layers. So when you apply pressure, you essentially are pulling the two layers together. And when you put them together, the hopping becomes a little bit bigger. And therefore, this interlayer coupling becomes a little bit bigger. And therefore, let's say all the electronic structure gets reproduced at a bigger angles. All right, great. So in short, this is how the electronic structure looks like. And let me emphasize that what I showed you before was just a sketch of what is the phenomenology. But now what I'm showing you here is how the true electronic structure of twisted graphene bilayers looks like. And this is something that you are going to compute in the afternoon, of course. So the basic idea is that if you take two layers together that are decoupled, then what you see is, well, the Dirac cones that are, of course, folded in the Redon zone, because you have now a very big supercell, but you see the very same Fermi velocity as the Fermi velocity that you would have, let's say, for each layer isolated from each other. This is in the case of in which the interlayer hopping is zero. But now, if you start switching on the interlayer hopping, what you actually do is you create anti-crossings in these bands, in the very same way as the anti-crossings that we saw for the one-dimensional moire, in the very same way as the anti-crossings that we saw for the twisted transitional metal dipole coordinates. And essentially, the magnitude of this anti-crossing is, again, the magnitude of the interlayer. And here you can very clearly see this notion of Fermi velocity renormalization. So in the absence of coupling, your Fermi velocity is very big, means that this slope is very, very large. But then once you introduce the coupling, you still retain the Dirac cones. So you still retain the crossings, but now the slopes are much, much smaller. And this change in slope is what is called the Fermi velocity renormalization. And another way of thinking about it is that switching on the coupling between the two different layers actually decreases the bandwidth between of the lowest energy states. And this is the very same phenomenology as we saw in the twisted dipole coordinates.
How do you determine the number of the layers of the banks in the second picture?
So how do you, sorry, can you say that?
Yeah, how do you determine the number of layers? Because it increases compared to the decoupled one.
Oh yeah, this is just because I kind of cut the plot at this energy, but let's say you continue this plot at higher energy, you see many other bands. And what happens from this plot to this plot is that some of the bands went just to lower energy. But of course, if you plot all the bands, the number of bands doesn't depend on your coupling. So you have the same number of bands, but they just move up and down in energy. Yeah, that was a very good one. Thanks a lot. All right, great. So then the idea is that as you go to small angles, then you get these mini bands here that have a reduced bandwidth, and that of course are going to become flatter and flatter as you increase the hopping more and more. So this is, for example, what you see here. So let me show you here what is the difference between the band structure for 1.5 degrees and 1.2 degrees. And you see that in both cases, you have, let's say, bands that have a relatively small bandwidth, but as you decrease the angle more and more, then the bands become get a bandwidth that is smaller and smaller. And of course, once you go to a specific angle, they get completely flat. And now, if you take the real values of the hopping in graphene, the real values of the interlayer hopping in graphene, what you actually see is that this limit in which the bands become completely flat appears around 1 degree, 1.1 degree, and so forth. And that is what is usually called the magic angle, which is the angle in which your bands are the flattest, mainly that the bandwidth is the smallest. It is not exactly 0, but it is the smallest. Sorry.
And in such cases, there's high interaction.
Yeah, and in that regime is where interacting states appear, which is what I'm going to mention now. Yes, yes, no, that was a very good point. And when you are at this magic angle in which your bands become the flattest, is when you can see many interacting states for the very same reason as we discussed before. So if your bands are flat, your density of states is very, very large. So any residual interaction that you have is going to drive a correlated state. If you have a residual interaction that is repulsive, it's going to drive some correlated insulator, maybe a magnetic state or a charge density wave state. If your residual interaction is attractive, it's going to drive a superconducting state. And if your repulsive interaction is, if your interaction is repulsive and you have a interesting property in the band structure, that is a topological property, you can end up with Chern insulators. And if your electronic interaction is repulsive and you have Chern insulators that you dope electrically, you can get a fractional Chern insulator. That is something that we are going to discuss in the session tomorrow. So the bottom line is that this emergence of flat bands in twisted bilayers are actually the fundamental ingredient to getting these different correlated states. And this just stems from the dramatically enhanced density of the states that you have in the system. The interactions in graphene have not changed. They are the same as they were all the time. It is just that now that your bands are flat, your density of states is much bigger, and the interactions can overcome the kinetic energy. And of course, something that is very interesting is that these minibands, they of course have moire states that are localized somewhere in the moire unit. So, and in particular, if you think about the flat bands that appear at the lowest energy, the bilayer graphene, they form an emergent triangular superlattice, as you expect from a moire system in a hexagonal system. But if you look at flat bands that appear at slightly higher energies, then the bands that you get, the states that you get actually form a hexagonal lattice. So at certain dopings, you are going to have correlated state in a triangular lattice. At other dopings, you are going to have a correlated state in a hexagonal lattice. And if you start playing with the twist angle with the interlayer bias, you can see both triangular lattices, hexagonal lattices, and Kagome lattices as well. And just because essentially all those lattices are compatible with the symmetry. So some flat bands are going to be localized in triangular, some flat bands are going to be localized in hexagonal, some lattices are going to be localized in Kagome lattices. And let me emphasize that this localization, different lattices, triangular, hexagonal, and Kagome, is not intrinsic of twisted graphene bilayer, but it also appears in twisted dichalcoid multilayer. So before we were just focusing on a triangular moire state, but with this triangular potential, you can create both moire states in triangular, hexagonal, and Kagome lattices, because they are, all these lattices are already imprinted in the structure somehow. So some moire states will localize in some regions of the unit cell, other moire states will localize in regions of the other. Here, so this is measured in terms of the interlayer hopping. So this would be charge neutrality. This lattice here would be essentially this flat one over there.
So I have one question on previous slide. So what controls the interaction to be attractive or repulsive? Is it electrochemical factor?
That's a really good question. And the short answer to that is we don't know. That's a So I mean, what you control the in experiment is different voltages. Let's say, and the voltages change your electron filling. The voltages can change also the interlayer bias that you have and so forth. And you can think that in these systems you have simultaneously many different interactions at the same time. So to start with, you have of course electron phonon interaction, and you have electron interaction. So you have attractive interactions coming from phonon, repulsive interactions coming from the electron interaction. But of course, when you compute effective interactions coming from Coulomb interaction, then you can also have attractive channels, right? So if you think that this system has magnetic ordering and there are magnetic fluctuations, then you could have an attractive channel driven by magnets. If you have charge density waves, you could have an attractive channel driven by charge density waves. If you have a long range Coulomb interaction, you can also have attractive channels coming from plasmons and so forth. So the answer to that question is we don't know exactly what is the exact nature of the attractive interaction and what are the exact inputs of the repulsive interaction. What is found experimentally is that just by changing these parameters, you go from a regime in which attractive interactions dominate to repulsive interactions dominate. Yeah, but this is of course one of the open questions in this problem, and of course also in many strongly correlated materials. Yeah, great. Thanks. That was also a pretty nice question. All right, great. So essentially, in this twisted graphene bilayers and in general twisted van der Waals material, we can create correlated states, not only in triangular lattices, but also in a hexagonal, Kagome lattices, and so forth. And given this, you now can think that in some of these twisted materials, you may get magnetic states, for example, in triangular lattices or in Kagome lattices. And of course, those are frustrated lattices that can give rise to quantum spin liquid states, as we discussed in the previous section. All right, so now let me tell you about some other feature of twisted bilayer graphene that it's not related with correlation, but that it's related with topology, actually, with this notion that you can have states that have a gap in the bulk and, let's say, protected excitation on the edges. And for that, let us look again at twisted bilayer graphene. But now let's analyze a little bit how the structure looks like. So the structure of twisted bilayer graphene has kind of three different regions in terms of structure. So in terms of how the carbon atoms are sitting on top of each other. So there's the AA region, in which all the carbon atoms sit on top of each other. And then there's the AB stacking, in which just one of the carbon atoms sits on top of each other in the BA stacking. And if you make a filling of your moire superlattice, according to regions that have AB, BA, or AA, you essentially see this kind of pattern. Now, this pattern is actually very interesting already in terms of the structural properties. So, as you know, in aligned graphene multilayers, you can have both AA stacking and AB stacking. But AB stacking has a slightly lower energy than AA stacking, just because of van der Waals forces, just because of how chemical interactions between the different carbon atoms. So if you think in terms of structure, in twisted graphene bilayers, you are going to have a distortion that is going to try to maximize the size of the AB and BA regions and trying to minimize the size of the AA region. Because from the elastic point of view, you would like to minimize how much energy you have to pay from having the wrong stacking. And it's not wrong, just simply a higher energy stacking. This effect is especially important when you are at really, really small angles. So when you are at large angles, you can consider that the AB and BA regions are not large, and therefore it is not worth to make an elastic distortion of your lattice. But if the angle is very, very small, in particular around, let's say, 0.1 degrees, then these AB regions are very large, and then at this point, it is worth to actually making a distortion, try to minimize the AA. So from the structural point of view, once you go to very, very tiny angles, then the AB regions and BA regions grow with respect to the size that you would have otherwise. If you're at the magic angle, this is not too important. But the magic angle, the relaxations are not critical. Then once you go to very small ones, they are critical. And let me also mention that these flat band states that appear at 1 degree are localized mainly on the AA regions, and they leak a little bit to the AAB region. All right, great. So now that we have these different stackings in the moire unit itself, let us just look at how the electronic structure of this system is in the limit in which your angle is very, very small, namely the limit in which your AB and BA regions are really, really large. So you can start thinking about the electronic structure of the AB-BA regions itself. So this is very similar to the idea that we discussed at the beginning, where we essentially thought in terms of local properties of the stacking for the twisted 2D magnet. So now for this, we are going to think in terms of the local electronic properties of each region of space for the twisted magnet here. So if we think about an AB bilayer in which we apply a bias, we actually have something pretty interesting. So the electronic structure of AB stack bilayer is what you see here on the left. So you have your parabolic dispersion, and that it's gapless, and you have a let's say massive chiral term that is called. So now if you start applying a bias between the layers, so you start let's say making a voltage between the bottom layer and the top layer, what you actually see is that you can open a gap in this bilayer graphene. So in monolayer graphene, there's no way of opening a gap just with biases, but in bilayer graphene, if you apply a bias, you can essentially open a gap. And this is, of course, extremely interesting from the technological point of view, because what this actually means is that you can turn a system that is a metal into a semiconductor with a bias. And with this, you can imagine that you can very easily create, let's say, quantum dots in space just by applying local gates in space. You can couple them with one another. And let me emphasize that this gap in bilayer graphene is maybe one of the most flexible ways of engineering quantum dots in van der Waals materials, because you can create quantum dots without any disorder whatsoever. Quantum dots that you can change electrically just with a switch, and quantum dots with a gap that is actually controllable electrically. So this is, of course, something that is being very, very much explored, especially for quantum technologies. But today, let us just focus on what is the impact of the gap opening in terms of topological state. So essentially, the gap that you get in bilayer graphene can be controlled with the bias. So the bigger the bias, the bigger the gap up to a certain threshold that, let's say, once you go above that threshold, then the gap becomes smaller. All right, so now the basic idea is that this gap is actually not a conventional gap, but it's actually a topological gap. And by topological gap, what I mean is that whereas in the bulk, you do have a gap, if you look at a finite system, so at a ribbon that is infinite in the x direction and has a finite width, then you see states that are actually crossing the gap. These states that are crossing the gap are actually very similar to the states that we had for topological superconductors. They are very similar to the states that we found in other cases. They have a completely different topological invariant that we are going to discuss tomorrow. But for us today, what is actually important is that they do exist. And every time that you apply a bias in a bilayer graphene, you essentially create edge states at this. And let me also note one thing that is very important here, that the direction in which these edge states propagate actually depends on the sign of your bias. So if you switch the sign of the bias, namely that you go from, let's say, negative in bottom to positive on top to positive in the bottom, negative on top, you essentially switch the chirality of every single state. And also what is important is that this switching of chirality not only happens when you switch the bias, but also if you switch the stacking of your bilayer. So you can think that if you start with an AB bilayer like this, you apply a bias, your states have a certain chirality. And now if you displace one layer with respect to the other, the chirality of the states also changes. Of course, displacing one layer with respect to each other is not something that we can do controllably in a lab, but it's something that happens naturally in twisted bilayer graphene, right? Because we have these AB and BA regions, which effectively are regions of space in which the stacking is displaced. So in those regions of space, you are essentially going to see those states. So if you now focus just on the AB and BA parts of your twisted bilayer, and you make a tilling in space, then the tilling in space that you get is different. So magenta is AB, and this light blue is BA. So the basic idea is that when you apply a bias at every single interface between AB and BA, you are going to see this edge state, this topological states, just because the chirality of the topological state changes in between regions. So in short, this is the picture that you have at every single interface. Let me emphasize that this is not a consequence of the moire electronic structure. This just comes from a local understanding of how the electronic structure is. So in this AB stacking, you are going to get states propagating in one direction. And in the BA stacking, you are going to get states propagating in the opposite direction. So then when you compute the local electronic structure of the full twisted bilayer, let me emphasize that this is an actual calculation. What you actually see is that at every single interface between AB and BA, you are going to have propagating states all over the place. And this realizes what is called a topological network, namely a network of electronic states that each electronic state is one-dimensional. So you can think that each state here is just the edge state of a system, but when you put all these edge states together, you essentially get a effectively two-dimensional electron gas. So this electronic state is actually extremely fascinating because it is simultaneously one-dimensional and two-dimensional, right? So technically, this is a one-dimensional electron gas, so this is like a Lafniger liquid. But when you go at larger scales, you see that the system is effectively two-dimensional. And signatures of all these mixed one-dimensionality and two-dimensionality can actually be very easily seen in electronic transport experiments, in particular by doing measurement as a function of a magnetic field. It doesn't do anything, in short. So let's say at the energies in which these networks appear, there are no states in the AA system, essentially.
Actually, like you said here, they are helical and not spiral. So
yeah,
they are actually going in both directions everywhere, but there's a zero.
Yeah, they are not helical, they're pseudo-helical. Yeah, I will explain tomorrow what that's. Yeah.
I think there was some interpretation of this electricity in bilayers that explains the sliding of the two layers.
Yes, absolutely. So this sliding of the two layers also accounts for ferroelectricity. So I think that that ferroelectricity is related with the structural relaxation. So not with the electronic structure itself, but just by the atomic relaxation, with the atomic relaxation. But yeah, absolutely.
But, no, I was wondering, since they apply this to an team, and they basically can slide the here isn't happening the same as well. Any input, like in practice.
Yeah. Yeah, that's a very good question. The short answer is that here it doesn't happen because here you don't have, let's say, local ferroelectric polarization. So in those systems, you can, let's say, move domains with a gate because you have finite electric dipoles that come from the location of the atom itself. So electric field couples directly to that. Here you don't have a finite polarization, therefore the domains do not. Yeah, that was a pretty nice.
What's the thing that happens in PCs? Is that the electricity used by structural relaxation? I understand the electricity is within the domain, but the construction matters at the edges. So what is actually using the electricity?
For the twisted HBM?
No, TVC.
For twisted HBM.
What's HBM?
HBM. So I mean, what is causing the ferroelectricity is essentially, let's say, mechanical relaxation of the whole structure itself. So for different parts of the structure, relax in a slightly different way. And the basic idea is that in HBM, let's say B has one charge, N has the opposite charge. So let's say intrinsically you already have plus and minus. And the basic idea that if you make the right distortion, then you are capable of creating finite electric dipoles. Yeah. Yeah. Thanks. So in principle, yeah, I mean, that could also happen. So let's say the deal here is that you get kind of, let's say, topological insulators. And I know that we didn't go into that, but let me just say that you have electronic states that have a gap in the bulk and chiral edge states in each different domain. So each different triangle here is a different topological insulator. And I mean, of course, the very convenient points for twisted bilayers is that when you apply a bias, the let's say the chirality of the states changes from domain to domain. Or in other words, the topological invariant changes from domain to domain. But of course, this is not only something that could happen in twisted bilayer, but could also happen in any other material. So if you have a twisted material that has domains, and each domain is a different topological insulator, then you would also see a network of states. So if you think in terms of topological superconductors, if you have a twisted topological superconductor in which some parts of your moire have one topological invariant and the other parts of your moire have the opposite topological invariant, then you would also see a network of these states. So I think that that has not been observed so far. What has been measured experimentally is this network of states in twisted bilayer graphene. But yes, that's something that could happen generally in any twisted system, of course. Yeah. Also, yeah. Oh, yeah. Yeah. So that can also happen. So due to let's say structural relaxation. So in those cases, the states are not topological; they are just kind of quantum well states of products there. So it's a little bit different from this. Yeah. Yeah. Great. Thanks for all the questions. That's great. All right. Great. So in the last 2 minutes, let me tell you about other twisted graphene multilayers. And the basic idea is that apart from twisted bilayer graphene, you can of course put as many layers on top of another as you want. And in principle, the limit to this is just, let's say, your imagination and of course time. But among the many different twisted graphene multilayers that you can have, let me just mention two of them. One is twisted graphene trilayer, and the other is twisted graphene double bilayer. So the twisted graphene trilayer that I'm going to tell you about is a twisted graphene trilayer in which the top layer is aligned with the bottom layer, and the one in the middle is twisted. And then the twisted graphene double bilayer, that you could call it twisted graphene tetra layer, actually consists on one bilayer that is aligned, another bilayer that is aligned, and then you twist these two bilayers with respect to each other. So the idea is that both these twisted graphene trilayers and twisted graphene double bilayers also show, of course, moire bands and also nearly flat band states. So in the case of twisted graphene trilayer, you see that you have a very reduced bandwidth here for this band and also dispersive states. And then for twisted graphene double bilayer, you will get also nearly flat band, but now a gap opens up. So in general, actually, the electronic structure at low energies in twisted multilayers is much more rich than in twisted bilayer. So in twisted bilayer, you always got your Dirac points. You always got at the single particle level, at the very least, Dirac equation with a very much reduced Fermi velocity. But once you go to more complex graphene multilayers, you can go to situations in which you have simultaneously flat bands and dispersive states, or situations in which you got a gap, a charge neutrality, even without producing any interaction, just coming from single particle physics. And let me emphasize that, of course, during the exercise session, you will also do these things. Now, let me tell you about two very interesting features of these two twisted graphene multi-layers. Let's start with the twisted graphene double bilayer. So one very nice feature of twisted graphene double bilayer is that this gap that you observe here, it also appears at relatively large angles. So even when you are at the 10 degrees and so forth, and the origin of this gap is actually just a single particle gap that comes from what is called crystal field effects. So what this actually means is that when you have 4 layers, actually the 2 layers in the middle are slightly different from the 2 layers on the top, in the sense that the 2 layers in the middle feel more carbon atoms surrounding them than the layers that are at the very top and at the very bottom. So if you think in terms of electrostatics, just in terms of, let's say, how much charge each electron feels around it, layers in the middle are going to feel more charge than layers in the top and bottom, and therefore their on-site energy is going to be different than the on-site energy of the outer layers. So if you think in terms of electric fields, what it's actually going to happen is that in this twisted double bilayer, you are going to have a built-in electric field for these 2 layers in the up direction and for the other 2 layers in the down direction. So the structure itself creates an electric field in the double bilayer. And if you think now in terms of the topological properties of a biased bilayer, what this actually means is that the structure itself is opening up a topological gap in a twisted double bilayer graphene, just from an intrinsic built-in electric field coming just from single particle physics. And of course, what is a very nice experimental is that one can apply also electric fields here and change what are the respective gaps of one of the bilayers with respect to the other bilayer. So this essentially allows you to have a multi-layer graphene that intrinsically has a topological gap, but that you can also control externally. All right, great. So that was all. Yes.
So here you don't have your values, so
Yes, exactly. It is created by itself. Exactly. Due to this, it's exactly due to the structure. So the structure itself creates an electric field. All right, great. So all that phenomenology is just single particle physics of this twisted double bilayer. Now let me tell you a little bit about this twisted trilayer graphene. So the twisted trilayer again has, let's say, very flat bands that can give rise to correlated states. You also see correlated states in the twisted double bilayer, of course. But let us focus on the correlated states in this twisted graphene trilayer. So of course, in twisted graphene trilayer, one also sees correlated states that open gaps in these near the flat bands and correlated states that give rise to superconductivity. Now, the very fascinating thing of this superconducting state is that it's actually spin triplet superconducting state that we discussed in the superconductivity session. And there are even some signatures of nodal superconductivity in this twisted graphene here. So in other words, by going to other twisted graphene multilayers, even though you may think that having flat bands may be kind of very similar in terms of physics, you can actually find correlated states and superconducting states that you may not be able to find in the smallest multilayers. And I think that this case of spin triplet superconductivity is one really beautiful example of this, because spin triplet superconductors are insanely hard to find in nature, and it is really inspiring that just with a twisted graphene trilayer, you get this really exotic superconducting state. All right, so this is essentially everything that I wanted to tell you today. So again, for the exercise session this afternoon at 1, just remember to download the Jupyter notebook from this address. And I made a few updates yesterday, so please try to download the latest version. And again, the idea for the afternoon is that you will have examples with some results, and you will have questions which we have to discuss, and also make modifications to the code to answer certain questions. So this is everything on my side. So see you at 1.